Welcome again to the next lecture. And if you remember the last lecture, we discussed about the degree of freedoms, and we discussed certain examples, simple pendulum, double pendulum, and all sort of example which can clearly explain what do you mean the degree of freedom. That is the number of coordinates you need to completely specify the configuration of the system, and that is the motion of the system. So now we in this lecture we're going to discuss a very important concept, which is the generalized coordinates. So if you remember in the Newtonian mechanics that when the system are not constrained, so what we do, we write the differential equation depending upon the Newton's second law. That is, if the force, for example, if you see here the external force which is acting on the system, or the internal forces, altogether the effective force is going to give you this rate of change of momentum. This is your Newton's second law. So but if the system is not constrained, so what you do is like all the component of the forces and the displacements are independent to each other, because when you constrain the system, then the coordinates are not independent. So earlier, when you don't constrain the system, you can write this, the force is if force is going to have a component fx and fy and f z, and this say displacement, this is r, is going to have this xi, yj, and zk if the system is not constant. So I can write like fx equal to this m d2x by dt square. I can write fy equal to m d2y by dt square, and then this similarly I can write for fz. So I can write because why I am able to write these two independently, because I know that x, y, and z, these coordinates which are specifying the system, are not constant and they are independent. But when the system is constant, the problem is that these ri, which are, that is x component x, y, and z, are not independent to each other. For example, if you remember, in case of the simple pendulum, this is x square plus y square is l square. Okay, so this is x and y components are not independent. So when you put the construct restriction on the system, two difficulties are there. First, we are not these equations are not all independent. The second one is that that the force exerted by basically when you see the dynamics of the system, that what you see, you are applying a certain force to the system, and then the system starts to move, do certain dynamics, and then is there possibility that when you stick the system, would you not able to identify the force, what kind of other forces are acting? Because of when you constrain the system, because of the constraint you are implying on the system, there are, depending upon those constraints, there are the certain forces which are acting on the system. For example, if a block is like on a surface, if your constraint is there is a friction. Okay, so if I pulling or pushing that block, so the friction force is acting on that system. That is because of the constraint. So the constraint on the system is giving a certain type of forces which are actually ad priori we are not going to know. So that what we want is, when we solve these differential equations which are not independent because of the constraint, we try to figure out that what those forces are there also, which are coming because of this constraint. So this is one thing which is two problem which is coming because of when we are constraining the system, a system being to do some limitations because of the constraint. So the first solution that the first, because of the first problem where the coordinates are not independent, they become dependent. So to get rid of that, we generally define the generalized coordinates. So what we're talking about is only for the holonomic constant, not for the non-holonomic constant. So when we are constanting our system with the holonomic constant, the first difficulty is solved by this defining this generalized coordinate. So you see that for a free particle, if this is like, consider for a free particle which is not constant, so it can have 3 degrees of freedom, 3 degrees of freedom, and can move along x, y, and z axis, and I can have this position vector depend on x, y, and z. Now the moment see, the moment I put the constant on the system, because if the constant is holonomic, that I am able to write the constant in terms of, like, say, if depending upon x and y, so this is going to be 0. So if for example, then we know that the degree of freedom is given by the number of particles in the system, in which dimension we are working, and what is the number of constant on the system. So we had discussed that if you suppose that this particle has to move on the circle, of radius r, then if we work in coordinate space that can specify in terms of x and y, I can write this restriction equation, that constant equation, that x square plus y square equal to r square, and z square equal to be 0, because in circle and we are talking about the 3 dimension, so z has to be also 0. So I have true constant equation, and 3 dimension, one particle is going to have 1 degree of freedom. So this is going to be have 1 degree of freedom, that is, it can only rotate along this axis, and that can be solved by defining a one coordinate, that is theta, which is independent. So that theta is, in our case, is the generalized coordinate. But if you try to specify the system in terms of xy, so this is not unique, okay, because for every x value you're going to give plus y and minus y. This is not a unique configuration of the system. So for this x value, the particle could be here or the particle could be here. So when you're applying a constraint, so it is restricting the motion as well as complicating the situation, and the coordinates which are specifying the configuration of the system are not independent, they are dependent. So what we are trying to do, we are trying to figure out that what is the one coordinate through which we can define the system, and that has to be unique. And in this case, theta comes out to be a coordinate which is going to completely define the system. So if the moment I say the theta is 45 degree or 90 degree, this particle is going to be here, because this 90 degree, this particle is not going to be at this position, because angle always we measure from this direction into anti-clockwise direction. This is going to be here at 270 degree. So theta is going to be the generalized coordinate, which is independent, which is unique, and which is going to completely specify or uniquely specify the system which we are dealing with under certain constraint, and that is known as the generalized coordinate. Okay. So generalized coordinates are the minimum number of independent variable or coordinates which we need to completely describe the configuration, which is that the system is in try to figure out what is the position of the system and what is the orientation of the system, of a mechanical system. That minimum number of variables which has to be independent, that is known as the generalized coordinate. So a system of n particles, which are, we know that is free from constraint, has 3n independent coordinates, because for that case 3 degree of freedom is there. And but if we have a holonomic constant, then this number of independent coordinates or degree of freedom is going to be 3n minus k. So please don't get confused with the degree of freedom, because we always define degree of freedom, we have defined degree of freedom as 3n minus k. And also defining the generalized coordinate, number of generalized coordinate is going to be 3n minus k. So but the problem is that this degree of freedom is unique, but the generalized coordinate cannot be unique. The generalized coordinate could be anything, that is okay. So degree of freedom number is unique, but generalized coordinate, like in cases theta, in other cases theta could be phi and anything else. So we will see in when we move forward. So mathematically how we define the generalized coordinate, because if you consider you have n number of system consisting of n number of particles, so and there are k constant, we are applying certain constant, and that constant are in terms of the equation that is going to give me the k equations. So this 3n minus k is independent variable which are going to define my generalized coordinate. So that is, and this has to be, it has to be in terms of the old coordinates, which by which were not dependent, which are becomes dependent by applying the constant. So that is, these are my q1, q2, q3, and this is how many number of coordinates are need to specify the system, and it could be a time dependent also. What r was going, when r was the coordinate, when you impose the constraint, then r is going to be dependent, and then we need these q's to completely specify the system. For example, if you see the recent example, the particle has to around the circle, that if you specify the system in terms of x and y, what you need is the x and y are not dependent. But if I define in terms of r and theta, then that is going to completely specify the system. But this x and y were not dependent, because independent, because y now depend upon r square minus x square plus minus. Okay, but the moment I choose this r and theta component, r is these r and theta are completely independent, and they are going to define the system. So r and theta in this case is going to be the generalized coordinate. But if you restrict the system, that is going to be on the radius of a particular radius, the moment the particular radius r is also fixed, and only the theta is going to be the generalized coordinate in this case. So the three we are going to have define the generalized coordinate with the term qj always, and j could be whatever this 1, 2, 3, and could be like up to 3n minus k. So like in this case we have only one generalized coordinate. This is going to be theta for this particular case. Okay, so let us try to figure out certain example which can define the generalized coordinate. First one is simple pendulum in 3s space. So as we have already gone through that, these are the two constant equations, and this is going to have the 1 degree of freedom depending upon the number of particles 1. So what it can have only one motion. So you see the degree of freedom is 1, and it can have one. There is one motion is possible, and that is completely defined by this theta. Okay, so that is going to be the generalized coordinate in case of simple pendulum in 3 dimension. Now we discuss also double pendulum in 2D and 3D plane. 2D plane we discussed that I'm going to have a two constant equation which is based on this L1, and the second one is on L2. So this is the second one is this. So 2 dimension, I have 2 particle, 2 dimension, and 2 constant equation. So 2 degrees of freedom is there, and that is going to be theta 1 and theta 2. So this theta 1 and theta 2, I cannot specify this system on the basis of x1, y1, and x2, y2, but because the moment I impose the condition that L is fixed, so these two equations are becomes x1, y1, x2, y2 are now dependent coordinates. So I need independent coordinates to specify the system. So these are my theta 1 and theta 2, because theta 1 and theta 2 is not dependent, they are independent. This is going to have a motion depending upon what is the angle theta 1. This is going to have the motion depending upon the angle theta 2. So this theta 1 and theta 2 is going to be the generalized coordinate, which is going to completely uniquely define what is the position of first pendulum and what is the position of the second pendulum, which is attached to the first one. If you talk about the second this double pendulum in 3 dimension, as I told you, that is in 3 dimension is going to be have 4 degrees of freedom, because the constant is same but the dimension changes. So I'm going to have this 4 degree of freedom, and this 4 degree of freedom is like this 2 are from theta 1 and theta 2, and 2 are from phi 1 and phi 2. They can have the different phi motion also, because you see that and so if I have x, y and z, and if this particle is there, it can have a theta and it can have a phi motion also. Okay, so it can rotate like this and it can rotate like this. So 4 degree of freedom for this double pendulum in 3 space. So theta 1, phi 1, theta 2, phi 2 are completely independent coordinates through which we can define what is at particular time, what is the configuration of the system. And these important thing is these coordinates q1, q2, q3, q4, which are defining this double pendulum, are quite independent with each other, not as x1, y1 and x2, y2 are now dependent coordinates the moment we restrict the system. The next example is like if I have restriction on this particle that it has to be on the surface of this inverted cone. So when we define a particle, position of the particle on this inverted cone, so this is in terms of the p, r, theta and phi. What is the r at particular position, and what is the theta? Theta is fixed, you know, this theta is fixed here, and this phi, what is the rotation of this particle. Okay, so this x, y, z component, as you know, in spherical polar coordinates are related with theta and phi. So because theta is fixed, okay, theta is fixed, so it's not going to because of this restriction. If we want to specify the position of this particle on the surface of this cone, so what I need is one is r. So where this particle is here, or this particle is here, this for this at this position is going to be this r, at this position is going to be this r. So r is not fixed, so it depends upon where the particle is, and the second is phi. So depending on where the particle is, what is the phi of that particle? Okay, that depends upon the position of configuration of the system. So because theta is fixed, one is fixed, and these two r and phi are going to completely uniquely give me the configuration of the system where this particle is located on this inverted cone. So these two r and phi are going to be the generalized coordinate. In case of a spherical pendulum, we have the restriction, one restriction, that is x square, y square, z square is going to be L square fixed. So we have 2 degree of freedom. So this particle, this pendulum can rotate along theta and can rotate along phi. So these theta and phi are going to be the two generalized coordinate in our case, which are independent. For dumbbell case, or as we talk about this center of mass, so in dumbbell case, in 2 dimension we have 3 degree of freedom. So you see here, one thing is very important in this case, dumbbell. So in this case, one option for the generalized coordinate could be like x1, y1. So the moment I have this x and y, so moment I fix this, so this is x1, y1, and say this is my x2, y2. The moment I fix this, okay, this is m1, this is m2. So moment I fix this, I can tell the position of what is the position of m2 by configuring this angle theta. Okay, so if I tell you that what is x1 and y1 and what is theta, you can quickly tell me that what is the position of m2. Okay, so this is one generalized coordinate, x1, y1 and theta. Or otherwise I can fix m2, and I can fix m2, and depending upon what is the theta, you can quickly tell me what is the position of m1. So that the second option for the generalized coordinate, which are totally independent, are going to be x2, y2 and theta. And the third option is there also when you talk about the center of mass. If I define what is the center of mass and theta, and that is also going to be the independent unique configuration of the system. So you see that degree of freedom is 3, but I have 3 options for the generalized coordinate. Rather, the number of generalized coordinate is going to be 3, but I have more options. So I have 3 options for the generalized coordinate: x1, y1 theta, x2, y2 theta, and the center of mass coordinate and theta. So there is a difference between what is the degree of freedom and what is the generalized coordinate. Okay, the number is going to be same. The degree of freedom is unique, but this the generalized coordinate is going to be different. It's going to be have certain options. So what else? Uh, what is this thing? Okay, so this is degree of freedom is unique, but the generalized coordinate is not unique. So I have this free particle xyz. So degree of freedom in 2 dimension is going to be, there is no restriction on the particle, and the particle number is 1 in 2 dimension. 2 degree of freedom is there. So in xy, so I am going to have the option of generalized coordinate x and y. Okay, see if I have 2 degree of freedom. So I have in 2 dimension, this particle is going to have completely specified by x and y. So that is going to have 2 degree of freedom. No restriction is there. So my generalized coordinates are x and y. And the second option for the generalized coordinate is r and theta, because I can also give the position of this particle when in terms of r and theta. So you see, degree of freedom number is 2, but I have 2 options for the generalized coordinate. It could be x and y, and it could be r and theta. But here in this case, you know that this system is free. In 3 dimension, in the same way, I have 0 restriction. 3 dimension, one particle is going to be 3. So I can explain by x, y, z, and also in terms of this r, theta, and phi. This is phi, and this is theta, this is r. So degree of freedom is going to be unique, but the generalized coordinates are not unique. So please don't get confused by what is the degree of freedom and what is the generalized coordinate. Okay, so I think the concept of generalized coordinate is like clear for you. If you have any doubt, you can always ask. You can always put in mail to me and for certain clarification and questions. Okay, the next is concept is for the configuration space. Okay. So this is very important because the first step in the formalism of Lagrangian dynamics is the definition of this configuration space. Okay, so configuration space is nothing but the space which is scanned by the generalized coordinate. You have, like, you define everything in terms of Cartesian coordinate, which is your physical coordinate, in terms of x, y, and z. But the moment you define the generalized coordinate to completely specify that system, then you are going to have different coordinates. So the space in which those coordinates are being there, that is basically the configuration space, and that space is the space or the system in which you do your Lagrangian dynamics we are going to do. Okay, so the configuration space is the space whose coordinates are the generalized coordinate. So in physical space, your coordinates are x, y, and z axis. You define the coordinate of this with, say, xi, yi, and zi, or this particle m2 by x2, y2, and z2. This is in coordinate space and physical space. The moment you restrict this system and then you define the generalized coordinate in terms of this q1, q2, q3, and whatever the number of generalized coordinates, so you move to a different space in which you treat the system in terms of the coordinates q1, q2, and q3, and then that space is known as the configuration space. Okay, so how to look the things? So each point in configuration space represent one possible state of the position. Okay, so like here you have this totality. This is a one configuration of the system consisting of these particle. But when you move to configuration space, so one point in the configuration space is giving you a one configuration of the system. Okay, the second point will give you the second configuration of the system. That is the difference between your physical space, or in terms, if you very crudely you think in terms of your Cartesian space and the configuration space. So each point in configuration space represent one possible state of the position of the entire system, and the number of independent coordinates equals to the degree of freedom of the system. So let's try to understand what is basically you mean by the configuration space. For example, if consider the simple pendulum in two-dimensional space. You see the degree of freedom is 1, and this is my generalized coordinate is theta, through which we can uniquely define the configuration of the system. But let's try to look the different space, the physical space and the configuration space. In physical space, what you do, if this pendulum is restricted to move in, like it will go, this pendulum will go from here to here and then come back here, and then it will go here and then it will come back here. Okay, so it is restricted to move along this half circle. Rather, you apply certain energy so it can go up and do the circular motion, the total circular motion. So in physical space, in x, in terms of the xy, in terms of the x and y axis, these bobs are going to have their position along this half circle. Okay. But you see the same thing in the configuration space, because the configuration space is the space spanned by the generalized coordinate. So generalized coordinate in our case is theta. So this is going to be a line, the number point of the theta. So if I plot theta here, theta angle on line, so what is going to be the position of these bob? So this is my mean position here, and then it can go like pi by 4. It can go here, this is my pi by 2, and then from here it comes again, and then here go minus pi by 4, and then here again that is going to be minus pi by 2. So this is pi by 2, pi by 4 mean position. This is my mean position, and this is my extreme position. Okay, this is my extreme position. So we see the difference between the configurations, how the points are being plotted. What is the position of my system in configuration space, and what is my position of the system in the physical space. In the same way, if you see the spherical pendulum case, this is my spherical pendulum in 3 dimensions. So it is going to have theta and phi as my generalized coordinate. So like in my physical space, this bob can have all sort of position on this surface. Okay, on this surface in x, y and z axis, it can have all sort of, it can be anywhere. Okay, but in configuration space, like theta can vary from 0 to pi, because theta, this can have 0 to pi angle from here to here, here to here. Okay, 0 to 2 pi, and then phi is going to have 0 to 2 pi. So in configuration space, this bob can be anywhere in this plane. Okay, every point on this is giving me where this bob is, whether this bob is here, this bob is at this position, or this bob is at this position. So any point in this space is giving me where the bob is there. So you see, this is my physical space and this is my configuration space. So any point in configuration space is defining the one unique configuration of the system which is there in the physical space. So I think it is very clear that what is the configuration space. It is just a space spanned by the generalized coordinate, which are independent, and it's going to have the number of degrees freedom. Any point in the configuration space is completely defining the one unique configuration of the system. So in this lecture, we have talked about this generalized coordinates and the configuration space. So I end this lecture at this position and this point, and in the next lecture we will talk about the generalized velocity, virtual displacement, and these are two very, virtual displacement concept is a very important concept in Lagrangian dynamics, and why we do this. So I hope you are getting my point and I'm clear to you very much. And with this, thank you very much for attending. Okay.